So today we're going to talk a little bit about resonance. And resonance is an increase in amplitude of oscillation of an electrical or mechanical system that is exposed to periodic force. And that force has to have a frequency that is equal to or a multiple of the natural frequency of the system. Consider for a minute an adult pushing a child on a swing. The adult in the picture pushes the child with the same frequency as the natural frequency of oscillation of the swing. And the result is that the swing oscillates with large amplitude. And that amplitude is going to increase because the energy that the swing needs to gain amplitude is being continually supplied by the adult at the right time in the cycle. Think for a moment that you're pushing a little child on a swing. And as you're pushing them, you need to step back because the amplitude of their swing is going to increase as you keep pushing and applying more force. The monkey on the right doesn't quite understand that, so he's applying the same force with the natural frequency of oscillation, but eventually, bam, he's shoved right out of the way. Because the pendulum increases in amplitude because the monkey is continuing to apply force, and then the monkey gets the force applied back to him. Natural frequency is the frequency at which an object will vibrate after an external disturbance occurs, such as the object being hit, struck, or otherwise disturbed. It depends on the elasticity, size, and shape of the object. And a natural frequency is a force vibration that occurs with very, very minimal energy. The tendency of one object to force another adjoining object. Now that object may be touching it or may be a little bit ways away, but they've got to be in close proximity to each other. So the tendency of that object to force another object into vibrational motion is referred to as forced vibration. And during forced vibration, the amplitude is intensified because a larger surface area is available to vibrate molecules. Examples are a mass on a spring, which you can think back to simple harmonic motion. Ringing small or large bells doesn't take much force vibration to get them to ring. Or rubbing the rim of a glass. If you just wet the top of a drinking glass and rub your finger on it, you can actually make it sound out a little bit or make the glass sing. Another example of resonance can be observed with the shattering of glass. If a singer produces a note at the same frequency as the resonant frequency of a glass, that singer can create vibrations in the glass. If they sing loud enough, they can actually produce larger vibrations, larger amplitude, and the glass may shatter. Thinking back to simple harmonic motion, we can also look at it with resonance as we make a bottle sing. When air is blown over the bottle opening, the air in the neck of the bottle behaves as mass on the end of a spring. So if you're looking at the diagram, the air in the neck of the bottle is actually what almost looks like an egg. So that elliptical area is meant to show where the mass of air, the mass that's going to oscillate within that bottle. And the bottle itself, the body of the bottle, acts as the spring. So you have the bottle as the spring and the neck as the mass that is oscillating. So this is kind of an upside down spring mass system as compared to what we were using when we had gravity acting to pull the mass down. The flow of air across the top of the neck of the bottle as the person blows pulls the neck mass, that little area of air in the neck of the bottle, out just a little bit. And that reduces the pressure within the body of the bottle. When you have lower pressure in the body, that neck mass of air is pulled back in. And so that little neck mass of air oscillates up and down as you blow across it. The rate of oscillation is determined by the mass of air in the neck as well as the size of the actual bottle. This system is resonant enough that it will respond to any sort of air disturbance with some oscillations at its natural frequency. We can also demonstrate resonance when we sing in the shower. This is an experiment you can do at home as you stand in the shower, because showers often reflect sound very well. Begin singing and slowly change the pitch just a little at a time. At certain pitches, the sound will suddenly amplify. It'll sound much louder because the sound waves fit an even number of times between the shower walls. So on the left, that's when you don't have the resonant frequency and the sound waves are all over the place. But then when they're at resonant frequency, you have standing waves created right between the shower walls, and it will sound the loudest. The sound will be amplified. An example you may be familiar with is Tacoma Narrows Bridge. This bridge collapsed November 7th of 1940, and the failure of the bridge occurred when a never-before-seen twisting mode occurred. When the left side of the roadway went up, the right side would go down, or vice versa. However, the center line of the road remained basically still. So imagine the center line is the equilibrium, with the left and right sides of the road acting as crests and troughs, oscillating up and down on either side of that center line. The original bridge was a suspended plate girder type that caught the wind rather than allowing the wind to pass through. So maybe think for a moment if you've seen signs, plastic signs on the side of the road and they'll have holes cut in them. And the holes are put into the signs to allow air to pass through the signs, because otherwise if you just had the plastic sign up and wind caught it, it'd pull it right out of the ground or off the trees, whatever the sign's on. So similarly, this bridge did not allow air to pass through it, it caught it. Initially, many people believe that the Tacoma Narrows Bridge collapsed due to residents. And when you read textbooks and much information online, that is what you're going to find. But more recent, and not completely recent, but more recent information has led scientists to understand that it was actually due to aeroelastic flutter. And the causing of the metal, the solid, to swing back and forth to create the waves caused the actual breaking or collapsing of the bridge. Watch the following video for more information. Keep in mind, resonance is all around us.